Alright, welcome back to another video. This video will be on projectile motion, and the purpose of this video is to start getting your feet wet in how to solve problems concerning projectile motion. This problem is just about as basic as it can get. When you start the problem, you read the problem. It says, on the surface of Earth we launch an object at 25 meters per second at an angle of 30 degrees. How far horizontally does the object travel? Well, you'd say, okay, well, I have this object being launched at 25 meters per second, so you draw your vector here 30 degrees above the axis, and you could go ahead and label it. Now, a very important thing to keep in mind is you also need to label your axis. You need to let them know, hey, what's X? Hey, what's Y? What's positive? What's negative? If you don't do that, how are they supposed to know? I mean, it's usually you could kind of assume, hey, this is going to be your X and this is going to be your Y, but there'll be a lot of problems where that's just something you're not going to be assuming. So you must keep in mind that you need to include your axis into your diagrams. So the first thing we're going to do is we have this vector, but it's in terms of its magnitude and its angle. We don't like that. We want it in terms of x and y components. So the x component will be here, and the y component will be here. Now for this y component, this is the opposite angle, so we're going to be dealing with sine. So the sine of 30 degrees is equal to this length over 25 meters a second. So in order to not be confusing, the sine of 30 degrees is equal to the y component's magnitude over 25 meters a second. So y, since sine of 30 is 1/2, multiply each side by 25, and y is equal to 12.5 meters per second. X. Well, this cosine of 30 degrees is equal to the square root of 3 over 2, and we're also going to be multiplying that by 25. So this one will be 12.5 square roots of 3 meters per second. And you could just leave it like that. It doesn't have to be an actual number. If you wanted to multiply it out, the answer would be 21.65 meters per second. That's really not that important. It's actually more accurate as 12.5 times the square root of 3 meters per second. It's not rounded off, it's exact in the sense we have it now. So we found the x and y components. Now what exactly are we supposed to do with them once we find them? Well, in the last video I talked about how if you launch something up at 12.5 meters per second, or if you launch something out and the y component happens to be 12.5 meters per second, both of these examples, both objects will stay in the air at the same amount of time. Only the y component is affected by gravity. Therefore, all we need to do to find the time in the air is simply just pull the y component out and analyze it all by itself. So we have 12.5 meters per second in the j-hat direction, or in the y direction, positive. Now we need to analyze how long this is in the air. Now keep in mind, when you fire an object up with 12.5 meters per second, it's going to fire up and slow down, slow down, slow down, and then right here it's going to stop, and then it's going to start falling back towards the Earth, and by the time this gets back to the Earth, it'll be negative 12.5 meters per second. So if we're interested in the total time up and the total time down, we need to incorporate negative 12.5 meters per second for our final velocity. Now, g is 9.8 meters per second squared, which we'll call 10 meters per second squared. Now, this is constant. So the acceleration that the object is feeling is a constant acceleration. So we can use our kinematic equations. The one we're going to use is Vf is equal to Vi plus At. Alright, so we need to first solve for t. So subtracting vi from both sides, we get at is equal to final velocity minus the initial velocity, and we divide both sides by a. We get time is equal to the final velocity minus the initial velocity. Well, the acceleration is g, and we're considering down negative, so we're going to put negative g in here. Now, what's the final velocity? Well, the final velocity will be negative 12.5 meters per second, because if we fire it up at 12.5 meters a second, it's going to go up, it's going to stop, and it's going to come back down. By the time it gets here, it will be negative 12.5 meters per second. It will. So that's our final velocity for the total time up and the total time up and the total time down. All right. So let's go ahead and place those values in. We're going to have t is equal to negative 12.5 meters per second minus a positive 12.5 meters per second for our initial velocity. And all of that is going to be divided by negative g. Negative g is always positive. Negative g is just is the negative portion is just saying in the negative direction. So we have negative 10 meters per second squared. Negative 12.5 minus 12.5 is negative 25. So we had negative 25 meters per second over, well, we could call it positive because the negatives will cancel, over 10 meters per second squared. 25 divided by 10 is 2.5. So let me change color so it don't get lost here. It's 2.5, and meters will cancel and one of the seconds will cancel. We'll be left with 2.5 seconds. So for the first portion here, all we've done was we found the x and y components of our vector. Alright, then we noticed, hey, we could just look at our y component. We could use that component to determine how long that ball is in air, because that's the only component that's being affected by gravity, so it must be the one that determines how long it's in the air. Once we determine the time in air, then we can use our x component to determine our horizontal distance. So the t is equal to 2.5 seconds. Alright, so we've used the y component to determine how long this object is in the air. And the third part of the question wants us to determine the horizontal distance displaced, or the horizontal distance traveled by the object. So we do know that the t, the time in the air, is 2.5 seconds. Alright? Now this part should not be challenging. What do we say? We said that, let's see, 1 second. We said that 12.5 square roots of 3 is roughly 21. So our initial velocity in the x direction is going to be 21.65 meters per second. Okay? So when this object is fired off at 30 degrees at 25 meters per second, our horizontal component has a velocity of 21.65 meters per second. And remember, we talked about how there's no forces acting upon this horizontal direction. In our physics matrix, our physics world, there is no air resistance, and gravity only affects objects vertically. It doesn't affect a perpendicular motion. It only affects vertical motion. So this 21.56 meters a second is just going to stay 21.56 or 21.65 meters per second. So after 1 second, he'll go 21.65 meters. After 2, he'll go 2 times 21.65 meters. After 3 seconds, he'll go 3 times 21.65 meters. So that's all that's really going on at this point in time. I mean, you don't even have to use any advanced physics, as you know that this rate is constant. This velocity is just going to be constant the whole time. So the distance traveled is just going to be your rate times your time. Notice your units when you multiply them across, and this rate you have here, which we can call this constant rate because it's never changing, versus this one where it is changing. The y component, it does change. The x component does not in these problems. So we could call that 21.65 meters per second. That'll be our rate. Our time, well, that's 2.5 seconds. Because we want to know how long or how far till it drops. Well, it's going to hit the ground in 2.5 seconds. So when we multiply these, you'll notice the seconds cancel and we're left with an answer in terms of meters, and that's our distance. That's our displacement. That's how far this object travels before it hits the ground. At the moment this object hits the ground, this is the distance the object has traveled. So what is this? Well, we have 21.65 times 2.5 seconds. So the distance this object will have traveled in the x direction, in the horizontal direction, or the I hat direction, is 54.125. We could say I hat meters. And remember, the I hat is just saying in the positive x direction. Now if it was negative 54.125 I hat meters, then it would be saying in the negative horizontal direction. So a quick recap, because these problems are really simple when you could understand that you're really just breaking a vector into components and handling components separately. So as a quick recap to clarify, you're given your problem. Some vector is something you're firing off for whatever reason, and it gives you an angle. You find your x and y components. You use your y component to determine how long in air. But you could use it for other things. You could also determine how high does the ball get to, like what's the maximum height. There's numerous things you can determine along this along the y component, but then the x component you can use to determine the horizontal distance. And there's more elegant ways of doing this, but as far as beginning your understanding of projectile motion, I believe this is where you want to start. You want to learn just to break the components and handle them separately, and when all the fog clears as far as what's going on in projectile motion, then we could really start to come up with some more elegant approaches to solving these problems. So for now, we're going to just do it this way. We're going to break it down into components and analyze the components as two separate one-dimensional problems. I hope you enjoyed the video. I hope it was informative. If anything I'm saying is confusing, or if I say something inaccurately, please post a comment to let me know. But I'll have some more videos out to you soon and try to clarify this tricky concept. It's really simple, but it can be tricky if you've never seen it before. So we're gonna work this through together and hopefully get you to the point where these problems become like 1 + 1 = 2. Thanks for watching.